Bismillahirrahmanirrahim. Hello everybody. This is worksheet number 10, real sequences. I will try to solve the most number of exercise of this worksheet. The first exercise asks us to give the definition about what we mean by UN converge to L. UN is a sequence, a sequence. Actually, this is equivalent, the characterization or the definition of the convergence of UN to L. For all epsilon greater than 0, we can research a rank which belongs to N, such that starting from this rank, we have the difference between UN and L is less than or equal to epsilon or strictly less than epsilon. This is the definition. This the first question. The second question, using the characterization or the definition, prove that the limit of 2n plus 3 over 2n plus 1 is equal to 1. 1n goes to plus infinity. We are concerned by verifying this characterization, this definition. Let epsilon be any given real number, positive. Can we find, does that exist a rank from N, such that starting from this rank, one has the difference between 2n plus 3 and 2 over 2n plus 1 minus 1 less than or equal to epsilon. We start from this absolute value difference between the limit and the general term. Here we have so with times we take difference and as usual, but we can write 2n plus 1 plus 2 over 2n plus 1 minus 1, and this gives us 2 over 2n plus 1. Here we suppose that it is enough, it is nice enough. This is less than or equal to epsilon. This means that 2n plus epsilon is greater than or equal to 2 over epsilon, which allow us to write 2n greater than or equal to 2 over epsilon minus 1, and this allows us to write n greater or equal to 1 over 2 times 2 over epsilon minus 1. If epsilon is greater or equal to 2, here we will get 2 by 2, which is equal to 1, and the difference is equal to 0. If epsilon is strictly greater than 2, this will be negative, and we know that in this case, in the case when epsilon is greater than or equal to 2, all natural numbers verify this inequality. So we are interested, it is more important to study for epsilon strictly less than 2 and greater strictly than 0. In this case, in the case 1 epsilon is greater or equal to 2, this will be negative. And all natural numbers are greater than or equal to non-negative real numbers. The most important is 1 epsilon is between 0 and 2. In this case, we win by finding the rank. It is sufficient to take the rank n of epsilon, which is the integer part of 1/2 2 over epsilon minus 1 plus 1. And starting from this natural number, we ensure that the difference is less than or equal to epsilon. The third question, they gave us value for epsilon. So they gave us value for epsilon. For epsilon equal to 1 over 10, we need to determine the rank. So the rank n of epsilon is equal to the integer part 1 over 2. 2 over epsilon is equal 1 over, so here we have 20 minus 1 plus 1, which is equal to 20 minus 1, 19, 19 and half, 9 and a half. This is equal to 10. From this rank, all the terms belongs to 1 minus 1 over 10 and 1 plus 1 over 10. The terms, so from this rank, all the terms belongs to this open interval. How about if we take epsilon equal to 1 over 100? In this case, we have n of epsilon, it is equal to 1 over 2. So 2 over epsilon, 2000 minus 1 plus 1, and the integer part, so 9 plus 1 equal to 100. Starting from 100, all the terms belongs to this interval. As I took in the inequality less than or epsilon, so here we can close the interval. If we want to take the open interval, so we take here strictly less than epsilon. The second exercise, evaluate the limit of the sequences un in each of the following cases. The limit of un equal to 2 over n power 3, un equal to n square over n minus 1, un equal to the square root of n plus 1 minus the square root of n, un equal to the square root of n squared plus 1 plus the square root of n over n plus 1, un equal to the square root of n squared plus 1 minus the square root of n over the square root of n plus 1 minus the square root of n, and finally un equal to 1 over n sine 1 over n. For the first one, for this one, un equal to 2 over n power 3. This goes to 0, 1 n goes to plus infinity. You can use the characterization, it will be very nice and very easy. For the second one, un equal to n square over n minus 1, un equal to n square over n minus 1. This is equal to n over 1 minus 1 over n, and it goes to plus infinity, 1n goes to infinity. For the third one, un equal the square root of n minus the square root of n plus 1 minus the square root of n, and this is equal, we times by the conjugate in this sense, so it gives us n plus 1 minus the square root of n times the square root of n plus 1 plus the square root of n over the square root of n plus the square root of n plus 1 plus the square root, and it is equal to n plus 1 minus n, so it is equal to 1 over the square root, and it goes to 0, 1, and goes to plus infinity. Yeah. For the third one, the fourth one, this one, un equal to, we have here n, the square root of 1 over n square, plus here we have the square root 1 over n, we have the square root of n from here, one over the square root of n. So if we times by n, we get n over the square root of n, which is equal to the square root of n, or divided by n times 1 plus 1 over n. We cancel this, and the remain goes to, when n goes to plus infinity, this goes to 1, this goes to 0, and this goes to 0 to 1, so we have 1. When n goes to plus infinity. About this. How about this one? un equal to the square root of n square plus 1 minus the square root of n over the square root of n plus 1 minus the square root of n. To check if it is true. Yeah, it is true. In this case, we can, for example, times by this is times by the square root of n square plus 1 plus the square root of n over the square root of n square plus 1 plus the square root of n times by the conjugate of this one, which is the square root of n plus 1 plus the square root of n over the square root of n plus 1 plus the square root of n, which is equal, it gives us n square plus 1 minus n. This with this gives a times the square root of n plus 1 plus the square root of n over this one with the last one gives us 1 times, and the square root of n square plus 1 plus the square root of n. In this case, the limit goes to plus infinity, since if we take off n from here and we cancel n with n and the others, we have the times, so it goes to plus infinity. The last one for this exercise and for this video, here we use the squeeze theorem technique. We have sine 1 over n is less than 1 and greater than minus 1. So by time we multiply this double inequality by 1 over n, we get 1 over n sine 1 over n, which is less than 1 over n. And when n goes to plus infinity, this goes to 0 and this goes to 0. So un goes to 0 because it is between two sequences which goes to 0. Squeeze theorem or sandwich theorem. Thank you for this session. We will see you in the upcoming video.